Hello, my name is Andrew Golczynski. My colleague John Emanuello and I work in the Laboratory for Advanced Cyber Research, where we develop systems for autonomous cyber threat hunting. Today, I'll be speaking about some of our initial work on using text-style analysis to discover anomalous activity in mixed host and network logging. As you all certainly understand, our problem is a fundamental one in cybersecurity. Detecting intrusions on networks and hosts is a sensitive and evolving process. Signature and AI-based approaches to this problem must be constantly monitored and updated to account for adversary actions, as such solutions tend towards overfitting and excessive specificity. Additionally, such approaches tend to require intensive pre-processing to suss out relevant information in the data, and human analysts are required to interpret results. Ideally, we would like to reduce the amount of manual work required in this space, and to create more robust detection methods that can learn to discover anomalous behavior in an evolving way. Our approach here is to treat our network and host logs as simple text, embedding individual terms from each log, so for example, IP addresses, file names, registry keys, etc., and concatenating those embeddings to create representations of full logs. From these representations, for logs, we can apply a simple encoder-decoder or autoencoder architecture as an anomaly detector. To ensure everyone is on the same page with respect to our anomaly detection method, here is some brief background. Autoencoders are simple networks that compress their input into a smaller latent space and then reconstruct their input from those latent representations. This forms a sort of lossy compression scheme, which forces the network to learn relevant patterns for describing the data. Data that is similar to the training data will be easily passed through the network and reconstructed cleanly, but dissimilar data will be mangled if it's passed through the network, which indicates an anomaly. For these experiments, we leveraged the operationally transparent computing dataset, an open-source DARPA repository of logs collected from a synthetic Windows network with genuine red team activity, simulating a modestly complex intrusion with various TTPs. The OpTC dataset is provided in an ECAR, Extended Cyber Analytic Repository format, which provides information derived from typical Windows utilities, so sysmon, procmon, etc., in an action object paradigm with 58 overall features in the dataset. So action object may be loading a module or creating a process, reading a file, something like that. And those 58 features are things like principals, users, images, file paths, registry keys, etc. This network is fairly extensive, with roughly 500 hosts. For our purposes, we chose to focus on 4 hosts, so numbers 201 through 204, with 2 being attacked and 2 being unimpacted by the attack. Unfortunately, our data is not inherently labeled, which stymies evaluation. So fortunately, the red team contractors did provide a general listing of their actions on the network, including some approximate timestamps and process IDs. From these, we were able to work through the data and provide labels, with any noted PID being labeled as malicious, and any threads or processes spawned by those processes being labeled as malicious as well. Additionally, some network activity was not directly or indirectly attributed to the PIDs noted in the red team documentation, even though it was malicious. So these had to be labeled manually for completeness. This was a very small amount of the data, though, so typically things associated with some miscellaneous network activity. This labeling is possibly overly broad. It's probably not the case that literally everything that a red team actor does is damaging to the system, so they're not necessarily malicious in that sense. But this approach should at least capture the malicious activity overall. We attempted to use a minimal amount of pre-processing, typically in line with NLP-style analysis. For example, stop word removal, trimming file paths to a single standard name, so sort of lemmatization in air quotes there, and bucketing continuous features into discrete values, so typically for network connections, here we have packet counts and connection lengths, things like that. For simple data cleanliness, we dropped roughly half the columns. So for example, record IDs, acuity scores from our collection system, memory from our stack info for memory, so on and so forth. And we replaced missing and low frequency terms with placeholders, so the null and obscure tokens you see there. This left us with roughly 5,000 to 8,000 terms per host, with records being 27 tuples over this vocabulary space. Now, our network architecture unifies a vocabulary embedding with a downstream anomaly detection task. Our input consists of a document. It's a single ECAR log record pared down to those 27 words from that 27 tuple I mentioned earlier. These terms are then embedded into an 8-dimensional vector space and concatenated, producing a 27 by 8, it's a 216-dimensional representation of the record. This representation is then sent through an autoencoder, compressing it down to 8 dimensions and then re-expanding it to 216 again. This reconstructed vector is then split into its 27 constituent approximate word embeddings, which the network uses to predict the original term in each position. These are given as probability distributions over the vocabulary. Loss is then calculated in two weighted components. The difference between our input document and our predicted probabilities at each position is given by simple cross-entry loss summed over all the words in the document. And also, a squared L2 loss over the internal encoder-decoder layers is added to this, as that provides for a faster, more stable convergence. For this experiment, we trained separate networks using 3 days of completely benign data on 4 hosts, roughly 15 million records per host. We then applied those networks to logs from the corresponding hosts over the duration of the red team attack. So that was another 3 days and 9 million records per host, give or take. We then calculated the cross-entry loss to discover anomalous activity in this data set. So for reference, our anomalous activity on host 201 was roughly 37,000 records out of the many million, and on host 203, there were 19,000 records we were looking for. On host 202 and 204, they were unattacked, so there was nothing to look for there. To demonstrate that our architecture is learning useful embeddings, we provide the following visualization. All of the term vectors for the log files are run through a t-SNE dimensionality reduction, which is then colored based on the term's role and meaning. For instance, the large red blob at the top of the figure consists of port numbers. Similarly, the orange and black blobs are registry keys and values, respectively. This shows that our network is learning to cluster terms based on their roles in the data. The large gray blob in the center of the figure consists of various file paths as they are manipulated, so moved around, read, written to, loaded as modules, etc., by processes in the data. We now provide an alternate coloring to demonstrate the structure of these files embeddings. Observe the .dll modules in red at the left side of the cluster. Additionally, note that the Microsoft Office files in blue are just below, so docx, PowerPoint, Excel files, etc. The larger orange cloud consists of various files pertaining to the Microsoft update process. The substructure in this cluster shows that our architecture is capable of learning some interesting structure in these terms, which means that the training process is giving us some amount of information here. To provide a general outlook on our results, we bucket our test data into 60-minute intervals and calculate the percentage of records in each bucket that are anomalous. So in this case, we consider a record to be anomalous if the cross-entropy loss is greater than the 99.9th percentile of the cross-entropy loss on the training data set. The horizontal dashed line here is set at the naive average expected level of 0.1%. That is, it's the number of anomalies we would expect given our choice of that 99.9th percentile threshold. Additionally, we calculate the number of red team associated records in each bucket. These can be seen here in red in the bars. On the morning of the attack, the anomaly score remains steady until the red team actor begins their work on the box. At this point, the anomaly score increases, only decreasing after the actor concludes their work. This correlation between malicious activity and our anomaly score could be used as a system for alerting cyber analysts to abnormal activity, and particularly anomalous records could be produced for investigation to allow the analyst to drill down into the issue. Similar results can be seen here for the other hosts. The attacked host's losses spike during the duration of the red team activities and are stable otherwise, while the unattacked hosts are relatively stable over the course of the experiment. A small feature worth noting, there is a seemingly unexplained spike in the metrics at t equals 1500 and t equals 2880, which is shared across all the hosts. So some investigation revealed that this was associated with an order of magnitude spike in Windows management instrumentation activity at those points in time. Now, it is true that the red team used WMI to move through the network, but it doesn't appear that this was explicitly associated with the red team's activities, at least given their documentation and our understanding thereof. So this gives us an example of a false positive, that is, an anomaly that is not malicious. This may be of general administrative interest for a sysadmin. These sorts of false positives are of concern for our team, and they'll need to be addressed and handled in later work. Here, we present the distribution of cross-entropy errors for the benign activity in blue stripes, as well as the distribution of malign activity in red dots. We can see that the red team activity is clearly separated from the baseline activity on the box, with activity on the far right of the diagram corresponding to actions taken by the red team actor using PowerShell Empire. By setting a threshold for anomalousness around that 99.9th percentile of the training data's reconstruction error, that we used before, we can achieve sort of high precision classification for anomalous data on this model. And I'll give you the exact numbers on that later. For reference, this is host 201, by the way. So again, to show the same graph for the other hosts, we see that the red team activity is more anomalous in general than the baseline activity, and the benign activity is fairly consistently distributed in all cases, which means that we have a good description of the sort of baseline. For these figures, we set a threshold at some percentile of the cross-entry loss for the test set. So this is on our x-axis, ranging from the 95th percentile to the 100th percentile of our test cross-entry loss. And we classify any record above that threshold as anomalous. We then provide the associated precision and recall curves for both attacked hosts with this precision, with this classification method, rather. The vertical dashed lines are at the 99.9th percentile of the cross-entropy loss on the training data, which is the same threshold used for the earlier temporal graphs. By setting these thresholds, we can discover an acceptable amount of red team activity without an enormous number of false positives. So to sort of go over the numbers here, host 201 and 203 were attacked. So we can see on 201, there's 80% precision at our set threshold with 66% recall. Host 203, lower precision at 66%, but a higher recall at 86%. Given the small number of actual red team records that we're looking for, it's not an awful showing here. Also worth noting, so 202 and 204 were not attacked, so these graphs are a little more boring in that case. So we would really like to report instead these sort of false discovery rates. So we would expect that to be around 0.1%, just because that's where we set our threshold at 99.9% of the reconstruction error. So on host 202, we get about that 0.082%. Host 204 similarly 0.096% false discovery. So in the future, we hope to improve on this work in a few ways. So unfortunately, record level analysis of these phenomena is not sufficient to capture the truly complex activities spread over a large window of time and memory. So some form of data aggregation will be necessary to discover these non-trivial attacks. For instance, we're working on aggregating logs associated with unique processes to provide greater context for our algorithm to work with, as that may provide better insight into end-user actions. Additionally, we're working to provide more realistic labeling and data. We're hoping to provide labels for the rest of the 500 hosts on the network so we can expand our work with our current data sources. Also, though, we are hoping to find ways to leverage implicit labels as proxies for anomalous behavior. For instance, we're looking at finding anomalies in individual users' behaviors, since that could help us to catch malicious actors impersonating legitimate users, while not requiring massive labeling efforts for training data production, seeing as we don't have to actually give labels, we just have to know what user is doing something. As with most other AI efforts, we're also looking at ways of handling dynamism and novel items in our data. So most networks aren't static enough to just train once. New items, so file paths, files, etc., IP addresses, registry keys, are going to be constantly appearing. And we can't just uniformly declare that new things are anomalous. So we need some sort of coherent strategy to handle those. Thank you for your time. So feel free to reach out to the team as needed with questions, concerns, or opportunities, or if you're interested in the data and the labeling we did there for. So thank you very much. We appreciate it.